Welcome to lesson 5 from chapter 3, Pure Mathematics Year 2, and this is all about functions. And today we're going to look at sketching graphs of modulus functions. So we've met modulus functions already, but we're going to have a look a little bit more in depth at the sketching, and particularly when transformations are involved. So that would be objective 2. So we're going to look at combining two or more transformations on the same curve. And we can apply this to all the different types of functions that we've looked at so far in this course. So the first focus will be on two different types of modulus graphs. So where the modulus is outside of the function f of x, and the second type where we take the modulus of our input x and then we apply the function to it. So there's two variations there, and then we'll also have a look at some more transformations. Okay, please pause the video, try the 4 warm-up questions, and then we will proceed with the lesson. Okay, so now you've tried the warm-up questions, let's have a look at the solutions. Right, so question 1, we have to sketch the graph of a quadratic, and we're allowed all real numbers for our domain, which is good, so we need to keep an eye on that. There's no restriction, and we also need to discern what the graph will look like without having to plot a table of values. We're not doing that anymore. We have to just use our brains and understand how to read the function itself. So we have a quadratic. Now, immediately by looking at this, we can see there is a y-intercept at +3. So we can indicate that on our sketch straight away. Perhaps we'll put that somewhere there just for now. We could move it later. We don't know. We'll just wait and see. What else do we know? Well, we also know the orientation. We also know that it's a happy graph. Okay, we have this shape simply because the coefficient of the x squared is positive. Okay, and when I say the coefficient, it's the one that we don't write in, but that is a positive one. It doesn't say negative x squared or negative 2x squared or anything like that. So we know the orientation. We know it's a U-shaped quadratic. We know the y-intercept. We need to know a little bit more about it. So one thing we could do is we could see if there's any points of intersection with the coordinate axes. So, well, we've done the y-axis, but we could have a look at the x-axis. So just label these axes actually on here. So this is the y-axis and this is the x-axis. Does it factorize? Well, we can do a bit of rough work at the bottom. If I try and factorize my f of x, let's have a close look. We have +3, so it looks like we could have a factorization of -1 and -3. Is that correct? Looks okay to me. So we have x squared, subtract 4x plus 3. We have a factorization. So that locks our curve in place, doesn't it? So we can actually sketch this with no trouble at all. So it's going to be coming down this way, and it will go through the x-axis at two positions. So the first one here, where x is equal to 1, and also here, where x is equal to 3. So that gets us the shape. Now, we're not quite done yet, because in capital letters, I've asked you to state its range. Okay, now at the moment, it's not entirely certain what the range would be. And there's a couple of ways we can get the range. But our aim is to find the minimum value. And like I said, there's more than one way to find the minimum value. But we need to figure out what is this coordinate here that gives us this minimum point that I'm just showing with a dotted line. Well, using the symmetry of the curve, this is the first way of doing it. We could just take the average, the mean average of 1 and 3, which is of course 2. That's the halfway point. So I know that if I substitute in 2 into my function, I should get the minimum value. So let's do that. I can use the factorized form down here. So f of 2, shove 2 in. What do we get? Well, we're going to get 2 subtract 1, which is, of course, 1, multiplied by 2 subtract 3, which is, of course, -1. So it appears that the minimum will be at -1. That's good news. So we've got the minimum value. You could do it a different way, of course. We could complete the square. So just an alternative. We could write f of x, completed squared form. So the first thing to do is halve that x coefficient. So it'd be x subtract 2 all squared. And as you can see, straight away we get that coordinate of the minimum. So we know there's a minimum at the x coordinate 2 straight away. And then we have to figure out what the constant would be. Well, if I actually work out x subtract 2 all squared, this bracket here, that will give me x squared subtract 4x, but I'll get a +4. I don't want +4, I want +3. So I'm going to have to subtract 1 to compensate for that. So by subtracting 1, I get the x squared subtract 4x +3 that I want. So once again, we can see that there is a minimum point at 2 minus 1. So that's really good. So to get the range, of course, what we need to do is we just need to read off all the possible y values we can get. Well, the minimum point is at -1, but anything else above that is valid in the range. So the range is simply going to be y is a real number, but the restriction is that y has to be greater than or equal to -1. Okay, and that's when we're allowing all real values of x. There we go. So that's the sketch. Now, and I've shown you a couple of ways of finding the range. Now, in question 2, it says use your response to question 1 to sketch this function. Okay. Now, you can try your ideas on a mini whiteboard. You've probably already had a go at this. If you weren't sure what to do, let's just recap what the modulus function actually does. So when you see the modulus function, i.e. you see these straight brackets on either side of the quadratic here, what that's telling you is that if there is any negativity in any of that function, so if any of the values that this function spits out inside these straight bars here, if any of this is at all negative, the modulus will instantly make those values positive. So let's have a look at our sketch. Is there anything on this sketch that gives you a negative y value, okay, or the value of the function is negative? Well, yes, there is, okay? It's anything below the x-axis. So anything below the x-axis down here is negative, and we can see that this part of the curve between the roots is, of course, negative. Okay, it's below the x-axis. So to sketch the modulus is actually really easy. We simply have to flip the, or I don't say flip the sign, but the graph is reflected in the line in the line y equals 0, simply because all those negative values, such as where the minimum point is at 2, -1, that -1 has to be made positive. So that has to be instantly flipped or just converted into a positive. So all we have to do, it's really simple. We'll draw it now. Now I've just waffled on a bit. So we draw our axes like this. Okay, so x and y and 0. And I'm going to sketch the curve again. So we had 3 as our y-intercept, and I'll just put the curve on first. So it's going to go down here like this and up like that. We had the points 1 and the point 3 as our x-intercepts. Now, what I've just mentioned, okay, this is obviously the graph of y equals f of x. Okay. Now, what I've just said, to get the function g, anything that's positive stays positive. The modulus function does nothing. But as soon as we hit any negative parts, those negative values immediately become positive. So it's going to do this. And I've not reflected it brilliantly, but that's a reflection in the line y equals x of any negative parts. So that's going to go up like that. Okay. And let's just erase the previous function. So we'll get rid of that. We'll get rid of that. And what we have here is a sketch of the graph y equals g of x, which is the modulus of f of x. And what's now interesting is we have a local maximum now. Okay, so where we had a local minimum at 2, -1, we now have a local maximum here at the point 2, 1. Okay, at that point there. So sketching the modulus of the function is actually pretty easy. You've just got to understand how to interpret the modulus itself. So that would be just a revision issue. Now for question 3, we've got a rather unusual looking function here. So we still have the same terms in a sense. We've still got the x squared, we've still got the -4x, we've still got the +3, but you'll notice that the x's are modulus. Okay, so we need to think about this in a slightly different way. And the way to think of it is, let's draw a table of values just to give us a clear intuition of what's going on. So I've picked out some x values here that we're going to plot in a moment. For the modulus of x, remember what the modulus does. It simply removes any negativity from the number. And to take the modulus of a number is really simple. So if we just write the moduluses in, so it's just going to be 5, 3, 1, 0, and all of these will remain unchanged because they are already positive. Okay. Now then, if we just do the positive part first, so for the y values, I'm going to start at when x equals 0. When x equals 0, the y value is just going to be 3. Okay, unaffected by any of the modulus stuff. When x equals 1, again, the modulus has no effect. So it's just the same as if I was finding x squared subtract 4x plus 3. So I just have to plug in the values. So if I do that, I'm just going to do that here. So h of 1, I can treat as 1 squared subtract 4 times 1 plus 3. Okay. Now, of course, 1 is where one of the roots was located. So you'll see this just confirms it. So we do 1 subtract 4, which is -3 plus 3, which is 0. Okay. So that's the point 0. And when we go to 3, that's the location of the second root. Okay, so without doing any more work, we know that if we plug 3 in fact, we'll just confirm it. So h of 3 is equal to 3 squared subtract 4 multiplied by 3 plus 3. So that's essentially 9 subtract 12, which is of course -3 plus 3, which is 0. Yeah, so all confirmed. So we've got 0 and 0. And then when we put 5 in, h of 5, what do we get here? Well, we get 5 squared, subtract 4 times 5. Okay, and then we have to add 3. Okay, so 25 subtract 20 is, of course, 5 plus 3, which equals 8. All right, so we've got our values there. Now, first of all, I think let's plot these points on the diagram first. So when x is 0, and we can just use a 1-to-1 scale for this. So I'll just fill that in. So we'll have the origin here, and we'll have 1, 2, 3, and 4. These are our x values, of course, and 5, which just fits on, I think. Okay. -1, -2, -3, -4 and -5 just there, and -1, 1, 2, 3, 4, 5, 6, 7, 8. These are the y values. Now, if we just plot those points, 0, 3. Okay, so there's the y-intercept, which we saw earlier. 1, 0, which is the root. Okay, 3, 0, which is the second root, and 5, 8. 5, 8 will be up here, although the line is missing. Okay, so that's the quadratic, and we also know from the work we did previously, if we put in 2 into this, that we get -1 as our answer. Okay, so that there would be a minimum point here at 2, -1. Now, just as a precaution, you might be thinking, well, hang on, isn't this a modulus graph? Well, yes, but if I just put that in, if we treat h of 2, remember, it's the actual x value itself that is being modulus, and 2 is positive. So it would just simply be 2 squared subtract 4 multiplied by 2, which is, of course, excuse me, 8. So that'd be -4 plus 3, which would be -1. So the fact that I've got a negative answer is not a problem. Okay. If you want to put 4 in, of course, you're more than welcome to do that, just to get a clearer sketch. So if we do h of 4, we get 4 squared, subtract 4 times 4, so that gives you 0, plus 3, which gives you 3. So it just helps you with the sketch, won't it? So at the 0.43, like that, and you just use the symmetry of the curve as well. So that would be the quadratic. Now I'm just going to try and draw this part of the graph as best I can. So just bear with me on this one. So it's going to come down like this, through the minimum point, up here, and through there. I can live with that. That's not too bad. So I've actually sketched, so far, I've sketched all of this section of the curve. Okay, all that is visible on the graph and nothing has changed. It was as if I have just sketched the graph, and I'm going to write it down here. It's as if I've just sketched the graph of y is equal to x squared subtract 4x plus 3. There's no difference. Now then, let's have a look at the negative part of this. So if you'll notice, because the modulus has taken effect here, when we take the modulus first and then plug it into the function, well, if I put x is -5 in, the modulus will make that 5, and I know my function will give me 8 because it's the same input as here. As when I put 5 in here, I got 8 out. So I get the same values. It's the same case with 3. So -3, the modulus becomes 3, so that will give me 0, and 1 will also give me 0. So we can now plot the left-hand side. So the left-hand side, I'm going to have -5 at 8 up there. I'm going to have -3, 0, -1, 0. And consequently, everything in between is going to behave in the same way. So if I put in -2, I'm going to get the same value as if I put in 2. So that's going to give me the minimum point. And if I put in -4, I'll get 3 again, as if I'd just put in 4, as we saw here, because the modulus would make it +4. So what's going on here? Let's finish the curve off. Now I'll do it in a different color so you can see the distinction. So I'm going to try and draw this. I'm not happy with that already. And in fact, I'm going to use a different color. Let's do this light blue. So I'm going to try my best with this. So it's going to come down here, through the minimum, up through these points. Oh, not too bad. So the whole graph Now this is the graph of h of x. So y is equal to h of x. And just to remind you, this is the modulus of x squared, subtract 4 multiplying the modulus of x, plus 3. So what's going on? So it's as if we take the whole of the positive side of the graph as normal with no change. This is as you would expect without the modulus sign. And then what happens is all of that just gets reflected in the y-axis. So everything is reflected that way, and it's a mirror image. And any of the negative coordinates, so the -1, which would have returned a value of 8, simply is discarded. All those negative x values in the domain are just discarded, and it's going to be a mirror image about the line about the line x equals 0, the y-axis of the positive side of the graph. Okay, so we can state the range of g and h now. So for question 4, the range of g, well, going back to g, g was the modulus function. Now that when the modulus was taken on the outside, so the range of g, which you'll be able to see on your page, but I can't, range of g would simply be all real numbers, but just to shorten it, we would be allowed to have y be greater than or equal to 0 because it bounces off the x-axis, okay, because of the modulus. Now for h, it's rather different. So ditto marks, the range of h is going to be, if you look at the diagram, it's exactly the same range as f was originally. So it's just going to be y greater than or equal to -1. Okay, simply because the minimum point was on the right-hand side of the graph, so that minimum point is retained. And it also says explain why g and h do not have inverses. Okay, well, the simple answer to this is just to do with the mappings. So if you look at g, and I can just show you this really simply. If we take any y value, so let's take a y value going across here. We'll look at h first of all, because that's in front of me. You can see that we have 1, 2, 3, 4. Okay, so there are 4 different distinct x inputs going to the same y output. So that would make h here, h is a many-to-one mapping. Okay, and we know that a many-to-one mapping, when you try and find an inverse of a many-to-one mapping, you have a one-to-many mapping, so you can't have a function. Okay, so the many-to-one mapping is a good enough explanation to explain why it doesn't have an inverse. Functions that have inverses are only one-to-one mappings, so you just have to show that they're not one-to-one. Similarly with g, this is also a many-to-one mapping, so they're both satisfying that condition. Okay, so that concludes the warm-up. Okay, so let's put some of these ideas together into a step-by-step guide of how to sketch modulus functions. So we're going to have a look, first of all, at the modulus of f of x, and what I mean by that is the modulus is on the outside of the function. So these are just my recommendations. There's no right or wrong way of doing it, but I do recommend these steps because in my head this makes logical sense, really. So let's just think of some arbitrary function. So I'm going to just sketch some axes here, like so, like that. So what we can do is just sketch. In fact, we'll put the axes on all 3. We'll do that straight away. So you guys can do this as well. And it's just something to refer back to. I know we're doing this 3 times, but you can look back and you can see when you're revising how to do it, what the steps are. So I'm just going to come up with just some arbitrary function, nothing special. So let's have a go. Something like this. So it looks a bit like a cubic. Okay. So we'll call this y is equal to f of x. Now then, so the first step, of course, is just to sketch y equals f of x. That's the first step. Without the modulus, just so we can see what the function looks like. And f of x should be something you're familiar with. It might have a transformation or two in it, but it was something you can sketch. Step 2, we have to look carefully at where the graph is negative. Now, I'll just refer back to my previous sketch here. You can see that the graph is negative both here and here, i.e. where it dips below the x-axis. Okay, so what we need to do now is I'm just going to redraw this and try and do it the same. So it's going to do something like this. Okay, so those negative branches, I'm just going to reproduce them. And so these parts here, so this negative part here, because they're negative, the modulus kicks in. So they are going to be reflected in the x-axis. So what's going to happen is, oops, if you just try and reflect that like so, so that the green highlighted bit is reflected in the x-axis. I've not really done a good job of that, to be honest. Let's try again. Like that. And then also where it dips below, where we have that local minimum, that is also going to be reflected here. Okay, so let's make a note. Okay, so we are going to, in fact, I'll write it over here. So reflect negative parts in the x-axis. And the last step, I mean, that's pretty much got, you've got the function finished, but to make sure that there's no confusion for the examiner, you need to delete the original function. So if we just focus on what we've got left of this, the function is, I'm going to draw over it pink. So this part that I'm going over now, this is essentially going to be the modulus of the function. Okay, as unusual as it looks, that's it. So it's going to be that pink line. So I'm going to reproduce that over here. So we just make sure we erase all the parts that it doesn't look anything like that, does it? Let me. So it's going to be something more like this. Okay, that will do. Okay, and we'll just make a note of what we've done here. So erase previous steps. So if you do this in pencil on your exam paper, there won't be any ambiguity. And we'll label what we've got here. So this is the graph. Y is equal to the modulus of f of x. Okay, and some of the properties of this, well, we can see clearly the range. Notable properties. The range is going to be, y value is going to be greater than or equal to 0. This is assuming, of course, there's no restrictions on the domain or anything like that, or there's no further transformations. But if you have a modulus outside a function, the values can only be positive or 0. It behaves in the same way as squaring. Okay, it's analogous to squaring because squaring also makes everything positive, but it also increases the amplitude as well. So that's how to sketch the modulus of f of x. Now let's have a look at f of the modulus of x, which we looked at also in the warm-up. Okay, so once again, I'm just going to draw a set of axes and we'll come up with some arbitrary functions. So we'll probably stick to the same one. This looks a bit like a cubic. So we'll draw some axes on here like that. Now, first step, just draw the function as it is, same as step one in the previous part. So I'll draw another cubic. So something like this again. So we'll just say sketch. So this is y equals f of x. And just sketch it. Y equals f of x. Now we've got to think about what happens when we apply the modulus to the x values. Well, I'll put the axes on and then we'll talk about what to do next. So put the axes on again, like this. Well, we saw in the example that the graph behaves exactly in the same way as, so I'm talking about the f of modulus of x now. This function would behave in the same way as f of x given here. So all this would be preserved, okay? Because all these x values are all positive. So the modulus function will have no effect on that part of the curve. So I can simply reproduce this part of the curve without any problem. So it's going to dip down like this and go up like that. Okay. So we're going to keep the sketch for, and this is not mathematically technical. This is just for your own notes really. For x is greater than or equal to 0. Okay. And for the reasons I've just explained, okay, the modulus has no effect on this part of the graph. Now, what happens next? Well, we've erased this side, so we'll just make a note. So erase the left-hand side, where x is less than 0. Okay, so you can delete that because that's going to change in the next step. For the final step, I mean, I've probably stretched this out to 2 to 3 steps, but you could probably do it in 2. As we saw from question 3 in the warm-up, now we've got our right-hand side all sorted because we know it doesn't change. So I'm just going to reproduce that again. It's going to do something like this. No change. We reflect in the y-axis. So this part is now going to reflect. So the positive branch, which we've kept in the y-axis. Okay, so I'll do that in a different color. So just a bit of symmetry. Something like that. Okay, so that's it. We finished. So that's the graph of y is equal to. In fact, I won't use the orange bit because it might get confusing. Just undo. So the whole sketch, I mean. So the whole thing is y is equal to f of the modulus of x. So as confusing and complicated as that looks, the sketching isn't actually too bad. Okay, so you have in your notes, you now have a step-by-step guide of how to sketch these modulus functions. All right, so for this worked example, I would encourage you to try this maybe on some rough paper before I go through it. So pause the video, see if you can sketch these modulus functions. So you have to sketch the original parent function, although it's not a parent function, but sketch the graph of the log of x plus 1, and then see if you can, once you've got that, sketch the 2 modulus graphs. Okay, so pause the video and try this. Okay, let's go through it. So the first thing we need to think about is, what does the modulus of x plus 1 look like? Well, we can do a couple of things here. We can just make a little mini sketch of the parent function. Now, when I mean parent function, this is what this transformation is based on. Because it is a transformation, because we have x plus 1 inside the function there. So parent function would just simply be the natural log, or y, just sketching the graph of y equals the natural log of x. Okay, if you wanted to sketch that, it's fairly simple. So x there, y there, and the graph would simply has an asymptote at x equals 0, and there's no other asymptote. It looks a bit like a square root graph in a sense. It climbs very gradually, but it doesn't converge, and it would cross the x-axis at the point 1. Okay, so there's an x-intercept at 1, and there is also an asymptote at x equals 0. Okay. Those are the main characteristics, apart from the shape, of course, to consider. All right, so, and this is y is equal to the natural log of x. So that's the parent function. Now, if we're going to sketch the natural log of x plus 1, this is simply translation. So let's just write down what we're going to do. So we're going to translate, so for part A, translate y equals natural log of x by the vector, and we'll write it in vector form. So if you just to recap as well, inside the function, it's x plus 1. Okay, so it does the opposite to what you'd expect. So rather than moving it to the right, as you probably expect by adding 1, it moves to the left by 1. And because it's inside the function, it's an x transformation. Okay, so it's going to be by the vector -1, 0, the bottom number, of course, representing the y direction. All right, so we can do that. So we just take our parent function and shift it 1 to the left. And I'll draw this carefully. So we'll draw our axes with a straight line like this. Okay, now if you'll notice, the asymptote of the parent function was at x equals 0. Okay, so it's kind of hidden on the parent function, but it's right here on that y-axis. That asymptote needs to shift 1 unit to the left. Okay, so we'll put that on first. I'll put that in orange. So it's going to be somewhere about here. Depends on your scale, of course. So we'll call that line x equals -1. That is now the asymptote. We now know that the y-intercept is going to be the origin, because obviously all the x values shift to the left by 1. And we can also tell this is true because if we plug in x equals 0, we get log 1, which is 0. So it cuts at the origin. And everything else we can just sketch as normal. So we just follow the shape again. So it's going to go up like this, and it's going to increase gradually like that. All right, so this is the graph of f of x. So this is y is equal to f of x, which I might as well write it on, which is equal to the natural log of x plus 1. Okay, and let's label the axes and everything else and do this properly. So x-axis there, the origin is here, and the y-axis is there. So I'm hoping that wasn't too strenuous. Now, this is the new stuff. So we can now take this information that we've got and apply our what we've just learned about modulus functions to this sketch. So the first job we're going to sketch. Now we've got the main graph. We're going to sketch y equals the modulus of f of x. So this is the first type of modulus graph we've looked at. So going back to our sketch here, well, the rule is, of course, that anything that dips below the x-axis is immediately reflected in the x-axis, okay, because we're not allowed to have any negative values whatsoever. So this is actually going to be really simple. So let's do it. So I'm going to recreate the sketch like so. So x and y will keep the asymptote, of course. So put it in the same place. X equals 1. Negative 1, sorry, x equals negative 1. And there's still going to be a y-intercept at 0. That point is still on the graph because 0 is part of the modulus. It's anything greater than or equal to 0, same as squaring. So we're going to keep this branch here. No problems with that. But all the stuff that I was highlighted in yellow is going to be reflected in the x-axis. So it's going to have this rather strange, sharp points to it, like that. And as strange as it looks, that is the correct sketch. So this is the graph of y is equal to the modulus of f of x. Just stick to the rules and you'll be fine. Okay, and it cuts at the origin. Or there is an apex at the origin. Okay, and finally, referring back to, of course, our first sketch, we're going to sketch the graph of y is equal to f of the modulus of x. So the modulus of x being taken first and then f applied to that. And again, what did we learn earlier? Well, we learned that the graph is unchanged for all positive x values. So I can keep everything as it was as long as x is greater than 0 or equal to 0 for that matter. So x is there, y is there. My graph is just going to be like this, essentially. Okay, so that's for, we'll put the origin on as well. That's for all x values that are positive. Okay, so I'm just referring to all this part here. Okay, we keep as it was. So I've tried to reproduce the sketch as it was on the previous diagram. But the interesting part now is that for the negative values, the modulus is taken and then the function is applied. So it's as if the graph is reflected. The positive part of the graph, I should say, is reflected in the y-axis. So it's going to do that. And again, it looks rather odd, but that's how it works. So this is y is equal to f of the modulus of x. Okay, and you can practice these, use graphing software such as Desmos GeoGebra just to check your understanding and pick a variety of different functions to practice your graph sketching. Right, so moving on to transformations. So I'm going to combine 2 or more transformations, and it's as many as you like, and there'll be a challenge later for you. So this activity, I'd like you to try it yourselves first. What you're asked to do is to sketch this graph, y equals the natural log of 1 subtract 0.5x. And it has to be a reasonably good sketch because I'm asking for points of intersection with the coordinate axes and any asymptotes. Right. Just as a hint before you start, it might help, I don't know, this is, perhaps it will, if you write the function in this way. And also, if you refer at the bottom of the page or the middle of this page, there is the order of transformations to help you. Okay, so what I've done there is I've just switched around the negative 0.5x and the 1. They're exactly the same function. Okay, I've just rewritten inside the bracket. Okay, so pause the video and try this. And you've got 2 attempts at this, and you can also refer back to Desmos or GeoGebra if you want to check your answer. Okay, so have a go now, please. All right, and let's have a look at how to do it. So the first thing to do is just to find out what the parent function actually would be. Well, I think it's pretty obvious. I hope that this is just going to be the natural log of x. So the first thing we need to consider is the natural log of x, which we've already sketched. So this is your first step, is to put this in here in this box. So we've got vertical line, horizontal line there. And again, it's a standard graph you'll need to know. And just to reiterate, the asymptote, there is an asymptote here. I'm going to overlay it over the top of the y-axis. It's the point, it's the line x equals 0. Okay, so that's where the asymptote is, which we have to label according to the instructions. So the parent function is going to look like this, and it's going to cut to the x-axis at x equals 1. Okay, so that's y equals the natural log of x. Now, if we refer back to the middle of the page for the order of transformations, you'll notice that the first 2 transformations involve the x coordinates, and there are no y transformations in this whatsoever. And it wouldn't make it too much more difficult by adding a y transformation. What's complex is the transformations going on inside the bracket. So the first thing we need to consider is the horizontal translation. Okay, are there any horizontal translations going on? Well, the answer is yes, there are. And whatever's happening to the x, the fact that it's being multiplied by a negative and 0.5, just ignore that for the minute. What we're interested in is the fact that this this weird looking x, not weird, but minus 0.5x is having a 1 added to it. So that tells me that the graph is going to move 1 unit to the left. So that's the first thing we need to do, okay? Applying the horizontal translation first. And let's just state that. So it's going to be a horizontal. In fact, I don't need to write horizontal. I can just write it as a translation. By the vector, or you don't even need to write vector, by the vector -1, 0. Okay, and we've already seen that in action, haven't we? So we'll do that again. So we put the x and y axes on here, and the arrows are a little bit interfering with this, but never mind. So moving everything to the left by 1 unit. So the asymptote is now here. So that's got an equation of x is equal to -1. And as we saw previously, this is now going to cut at the origin at 0. Okay, so we have just sketched the graph, and we might as well give it a name. So this is the graph y equals the natural log of x plus 1. Now, that's the first transformation applied. The second transformation, you have a bit of choice about here. You can either multiply your x by 0.5, or you can multiply it by -1. It doesn't matter. I've split them up into 2 possible transformations just to make it a little bit easier, I think. So we'll deal with that next. So we have to do all the horizontal stretches next. And the horizontal stretches, as I've just alluded to, is this part here. Okay, so what I'm going to do first is I'm going to multiply the x part by 0.5. And what that does, of course, is this is going to be a horizontal stretch or stretch in the x direction, if you like, scale factor 2. Okay, and why is it scale factor 2 and not a half? Because it's inside opposite. Okay, and you can see that from the table of the order of transformations below. So let's do that now, and we'll see how this manifests in the diagram. So we'll put our axes on here as we did previously. So we've got y, we've got x, and because this is a horizontal stretch, the y coordinates are not affected in the slightest, but all the x coordinates are going to double. Now, that includes the asymptote. Okay, so the asymptote is now going to be stretched scale factor 2, so it's now going to be at negative 2, x equals negative 2. So we'll put that on first. Now, the y-intercept is still going to be at 0, and the origin, and at the origin as well, because if you double 0, of course, you just get 0. So the graph is just going to look something like this. Okay. So I've now stretched its scale factor 2 horizontally. So we'll just indicate what we've done here. And this is the graph of y is equal to the natural log of 0.5x now plus 1. Okay, so we're nearly there. Now all I have to do is apply another horizontal stretch, but this time the scale factor is going to be negative 1. And you could have done this in the other order, it doesn't matter. Now, when I say stretch, it's not actually a stretch, because if you're applying a stretch scale factor 1, that doesn't do anything at all. If you're applying a stretch scale factor negative 1, this is effectively a flip in the x direction. So the entire graph is just going to rotate about the y-axis essentially. And then we should have our final result. So I'm just going to finish off here now. And like I said, you've got 2 attempts at this if this was done in class. So we've got y, we've got x, okay. And if we flip everything about the y-axis, the most obvious thing that is going to flip, first of all, is the asymptote. So we'll do that. So that's now going to be at x equals 2. I'll put that on this side now. And just label that. So that's at x equals 2. And the graph is just a mirror image. So it's just going to be something like that. In fact, let me try that again. I've not quite gone through the origin there, have I? It's going to be something like that. Okay. And there we go. So we'll just label that point of intersection, which is at the origin, and we'll just label the graph now. And we've got the finished product. So this is the graph of y equals the natural log of minus 0.5x plus 1 as required, or 1 minus 0.5x. So you've got to be very careful. You can break it down into several stages, but stick to the order of transformations. Okay, so the first transformation you always do is the horizontal shift, the horizontal translation, then it's horizontal stretching, then it's vertical stretching, and then vertical translation. Okay, right, so let's move on. Let's have a look at some worked examples on this. All right, so there's 3 examples in one here, and this is a really good exercise in testing your understanding of transformations without having to actually sketch any graphs. Now, we actually can't in this instance because we don't know what y equals f of x is, okay? We're basically just going to be following a point around once each transformation is applied. And we've got the graph y equals f of x, and the point we're interested in is the point negative 3, 2. And we've got 3 different transformation situations to figure out. So for part A, this is going to be P1 that we're going to find, the transformation when we apply 0.5x inside and 2 on the outside. So just to interpret what's going on here, let's just start for part A with just writing down the point P. Okay, so P is at -3, 2. Okay, now if we look at the transformation we've been given and the order, the first thing we have to do is consider, are there any horizontal translations? Okay, the answer is no. There's nothing added inside the function, okay, or subtracted. So that means that we can just ignore that one. There is, however, a horizontal stretch, okay, which is the part that I've just highlighted in yellow. So let's just do a little key here. So I'll just put a yellow blob. So we're just going to be talking about this horizontal stretch. And I'll just describe the transformation first. So it's a horizontal stretch, and you can use the table that I provided as well. It's the scale factor is 1 over that value. So the scale factor is 1 over 0.5, which is of course 2. So what that means is this only affects the x coordinates first of all. So this is an x transformation. And if you want a shorthand way of doing this, because I'm just writing out all the technical information, you just note that what happens to the P is that the x values, so to indicate the x values, I'll just do a little horizontal left and right arrow. In that direction, you simply multiply them by 2. Okay, so we can now apply our first transformation to P. So P is going to be translated, I'll call this P dash for now. It's not a derivative, it's just P dash. This is the first transformation applied. So what I have to do according to these instructions is in my x coordinates here, I have to double my coordinates. So that's going to become -6. Oops, so it will be when I turn the highlighter function off. So it's going to be at -6 and 2 still in the y direction. Okay, so that's the first thing. Now the next up, we're going to have a look at the second transformation, which is on the outside. So this is affecting the y direction. So again, I'll put a little green blob here just to explain what's going on. And just as a shorthand, we know this is a y transformation because it's on the outside of the function. Okay, so it's going to be in that direction. And we just have to decide what's going on. Well, the outside of the function, we have inside opposite, but outside is the same. So because the whole thing is being multiplied by 2, that's exactly what we do to our y coordinates. Okay, so this will give us our P1, okay, as requested in the question. So I'll just put an arrow over here. So this implies that P1 is going to be at the point with coordinates -6, which we've already done. And we also have to double our y coordinates as well. So doubling the y coordinates, we get 4. Okay, so in summary, inside opposite, so we double the x coordinates, and outside the same, so we double the y coordinates, and the 2 transformations are done. Now for part B, we can sort of go a bit quicker with this now. We have, again, we've got 2 transformations to consider, and we're starting again at the same point. P is at -3, 2. So we're not following on from what we've just done. We're going to start again at -3, 2. And first thing to notice is we've got 3 subtracted from f of x, right? So we're going to apply the modulus last because that's on the outside. So we first need to consider what's going on with the function before it was modulus. So we would have y equals f of x subtract 3. Now, what that means is that because we're subtracting 3, this is a vertical transformation again, and it just means that we're subtracting 3 in that direction. So it's going to affect the y coordinates only. So that's pretty straightforward. We just have to subtract 3 from the y coordinates. So I'll put a p dash again. Nothing happens to the x coordinates, but we have to subtract 3 from the y coordinates. So that's what I'm going to do. So if I do 2 subtract 3, that is going to give me -1. Okay. I hope that's clear, ladies and gentlemen. Now, we apply the modulus function now, and we're not going to be sketching this. So what does the modulus do? Well, the modulus is just going to make the whole function positive. So if there's any negative values in the y direction, of course, nothing to do with the x direction, in the y direction, any negative values are going to be made positive. So here we're going to apply the modulus, and consequently P2 is just going to be at the point -3, and the -1 now is now going to change again, and it's going to become 1. So it loses its negative sign like that. Okay, so we now have P2. Okay, and for P3, which is part C, we have quite a lot going on with this one. So again, we're starting at -3 and 2. And looking at the transformation, horizontal translations first. And there we have it. We have a +1 inside the function. Okay, so the first thing I have to do is, because it's inside the function, it's going to affect the x direction. And what I've got to do is I've got to subtract 1. So it's going to be applying this vector -1, 0. Okay, so subtract 1 from the x coordinate. So my p dash, if I subtract 1 from the x coordinate, that's going to take me to -4. Okay, and the 2 stays as it is. We only do 1. It's only affecting either y or x at any one time. Okay, the next thing, what happens? Well, the next thing we're going to look at is this transformation here. So it's the horizontal stretch. So again, we know it's in the horizontal direction, so I'm just going to indicate that. So left and right arrow means I'm working horizontally. And what am I going to do? Well, I'm going to multiply by inside opposite. So I'm going to multiply by 1/2. Okay, in my x direction. So my x coordinates are now going to be halved. And if I do that, I'm going to call this p double dash. If I halve my x coordinates, that's going to give me -2. Okay, so the x coordinate changes again. Nothing happened to the y coordinate yet. That will all change now. Okay, so moving up here. What do we do next? Well, we've now got the -1 on the outside, so that's affecting the y direction. So just make a note of that. It's going in the y direction. So it's in this direction here, up and down, and I have to subtract 1. So in other words, I'm just going to apply the vector 0, -1. Okay, so it's as you would expect in the y direction. If it's -1, that's exactly what you do. You're going to take 1 off the y coordinate. So that's going to give me my P3. So my P3, I just have to take 1 away from the y coordinate. So I'm going to keep the -2, and the y coordinate will become 0, just taking 1 away from 1. In fact, I've just realized I've made a mistake, haven't I? Let me go back. I don't know why I wrote 1 there. So that's -2, 2. I halved both of them when I said not to. And then here, okay, if I subtract 1, that should be 1, shouldn't it? Just write that in. And just check that's right. So just to review, trying to do too much at once there. So the first thing to do, we have the +1. Okay, inside the function, that means we have to translate it 1 to the left in the x direction, which is what we've done. So that took us to -4, 2. We then multiply the x coordinate by 1/2, which is what we did. Well, I did it wrong at first, so that's going to be -2, 2. And then we subtract 1 from the y coordinate. So we have -2, 1. Okay, so we have P1, P2, and P3. All right, so this is the final example, and I've set this as a bit of a challenge for you. So I would pause the video and spend a bit of time looking at this, and you can also check your answers using DesBoss or GeoGebra. But I will go through the solution on the board. So if you'd like to have a go at this, please pause the video now before I go through the solution. Okay, so we're going to do this in several stages, and one of the first things to do is to identify what the parent function is. So I can see an exponential in there inside those two modulus functions, and there's a lot going on in this. So the parent function, if I just make a note of this, in fact, let's use the pen function on here. So parent function, you've got some choices really with this. It depends how confident you are with your functions. So the first option for your parent function would be y is equal to e to the x. Okay, and if we want to sketch that, so I'll do that initially. So we'll do sketches of all this as we work through it. So e to the x looks something like this. Okay, and it's just a curve. It's a standard curve that you need to know. So it's exponential, of course, so it's going to climb for positive x values. It's got a y-intercept at 1, as all exponentials do, and it has an asymptote at y equals 0. So, okay, and the other thing to notice is that there are no negative values to speak of. So this is y is equal to e to the x. Now, if you're feeling a bit bolder, you could go straight for a different parent function, and the alternative would be to sketch the graph of y is equal to e to the modulus of x, and we've talked about this in the lesson. This is something we can quite easily sketch, really. So, for example, in case you don't see it, if I consider the function f of x is equal to e to the x, like that, then my input, of course, is just x, okay, and that's reproduced in the exponent for e. So, just to make a slight adaptation, if I take f of the modulus of x, like that, then I replace my x input in the power with the modulus of x. So this could also be a viable parent function, and to sketch that isn't too difficult. And in fact, I'm going to sketch it over the top of this parent function. So remember, when it's f of the modulus of x, we retain all positive x values and their function values as well. So the values of f are retained. So the bit that I've just gone over in red is kept. All right, that is exactly the same as it would normally be, because the modulus does not affect positive values. But for the negative x values, because the modulus is applied, we have the reflection in the line y equals x. So the red graph would be y is equal to e to the modulus of x, like that. And again, it's quite a simple function, really, okay, which comes to a point in apex at the point 0, 1. So I'm going to use that as my basis, my parent function. So the next step, so let's just sort of storyboard this, I'm just going to go across here. What can we do? Well, we have to perform the horizontal translation first. Now, the horizontal translation, which I can see, is inside the function. So I'm going to have a crack now at sketching the graph of y is equal to e to the modulus of x subtract 2. Sorry, x subtract 1 in the power. Okay, now to do that, I simply take my parent function, and the instructions are I have to move my parent function 1 unit to the left. Okay, or I can just say more mathematically correct, it's going to be a translation by the vector, or just by -1, 0. Okay, and I've just realized that that's wrong. Let me just redo that. I'm talking nonsense. Got my translation the wrong way around. Sorry, it should go that way, and the translation should be in that direction. I can sense you all screaming at the screen. Yeah, so -1 means I move to the right. Okay, so we can now sketch that. So I'll put that here. Okay, so we just moved my red graph 1 unit to the right. Now we've identified what's really going on here. So let's do that. So it's going to do something like this. Okay, and if we move it 1 unit to the right, we can see some clear information appearing. So we've got the point 1, 1 there, because if I move it 1 unit to the right, that apex, that inverted apex at 0, 1 is now going to be at the point 1, 1. And we also have a y-intercept that has just materialized. So we have a y-intercept here. So we need to figure out what that point is. So we just have to sub in x equals 0. So when x equals 0, what happens here? Well, we get y is going to equal e to the power, and it's all going to be modulus, of course. So the modulus of 0 subtract 1. Okay, so in other words, which equals e to the modulus of -1, and the modulus of -1 is just 1, so it's just going to be e to the power 1, which is just e. So that is e, about 2.71. Okay, so we're doing quite well. Now we've addressed that, we now move through our transformations. So there's no more x transformations to speak of. What we do have now, we have a y transformation here. We have to subtract 2 from all the y values. Okay, so let's move on to the next step. So let's do that. So I'm just moving over to here. So now we're going to have a go at sketching y is equal to e to the modulus of x subtract 1, which we've just done successfully, I hope, and then we're going to subtract 2. So we just drop the graph down by 2 units. I'm just going to do that straight away without too much hassle, I hope. So I'll put that here, and I'll do the axes in black like I have been doing previously. So everything's going to drop by 2. So let's see what happens. So if you notice, my y-intercept is at e. I'll just leave that for now. But for that apex there, that's 1 unit there. So I'm going to have to go 1 unit below to drop by 2. So my apex is going to drop to -1 on the y-axis. So I'm going to indicate that on here. So that's going to be -1. And it's not shifting left or right. So it's still going to be the apex is, or the line of symmetry is still going to be along the line x equals 1. That's fine. So let's just sketch this in. In fact, I think I need to move that up a little bit. So I'll just move those and I'll sketch the curve first. So it's going to look like this. Draw this correctly. Okay, that's not too bad. So let me just relabel that. So this point here will now be at -1 because it's now dropped by 2 units. So we just go back, that's 1 unit and that's another unit. So this is now at -1 here. Okay, and my scale is slightly different on the graph on the right hand side. Now my y-intercept has also dropped by 2. And if you know anything about E, in fact, I just mentioned it, is 2.71. So if I subtract 2 from that, it's going to be about 0.71. But I'm going to leave it exact. So that's going to be E subtract 2 as my y-intercept. And I'll just also indicate this line of symmetry here is at x equals 1. Okay, so we're nearly there, ladies and gentlemen. So all I have to do now is take the modulus of all of this and we're complete. So another arrow. So my storyboard continues. So down to here, we're now going to sketch the final thing. So we're going to take y is equal to the modulus of the whole thing, e to the modulus of x subtract 1, close the modulus, subtract 2, and close the second modulus. And now we've got all the transformations done. It's just a case of taking the modulus of what we've got. Well, all we do is we say, okay, we just replicate the curve. So anything that is positive is kept, but anything that is negative is reflected in the x-axis. So it's going to look like a W shape like that. So I'm just going to sketch that as my final thing. So I'll put it on here. So notice all the skills on show here. I mean, it's a bit of a challenge, really. And I'll label my axes this time. So X and Y and 0. And I'll do it in green again. So it's going to look like this. So it's going to come down like that. And then it's going to arch in like that to a point, come down again, and then arch out, something like that. Okay, and I can label all those key points now. So the mirror line is still at 1. Now, because the minimum point was at -1, this is now going to be at +1. In fact, my sketch should probably be a bit more accurate than that. So let me try again. So it's going to come down like this. Okay, and yeah, I think that's better. And I'll explain why I did that now. So the point here, of course, is E subtract 2, which is about 0.7. The apex here is at 1, so it needs to be a bit higher up. That's why I resketched it. So that's going to go in about there. That's also going to be the point 1, the mirror line. And there's a couple of points that we haven't actually identified, which are the X and Y, the X-intercepts. They've kind of been neglected. So the X-intercepts, which are here, which is where this function actually bounces off. So we can see the range is clearly going to be all positive numbers. So we need to think about what these X values will be as well. All right, so to find the X-intercepts, how do we do that? Well, we can actually probably do that using the previous step. We don't need to worry about the whole function being modulus because that's irrelevant. And in fact, if we set an equation where we have the modulus of all that is equal to 0, then it doesn't matter. You might as well just set the function equal to 0. Okay, so we can actually identify what the roots are. So I'm going to take, I'm going to solve the equation and I'll explain why. E to the x subtract 1 minus 2 is equal to 0. Okay, and then we can do a bit of graphical reasoning. So what that means is, of course, that e to the x subtract 1 must equal 2. And if we take logs of both sides, we get x subtract 1 comes down, ln of e is equal to the natural log of 2. And then ln of e is, of course, just 1. So this term is just 1. So if I add 1 to both sides, that gives me my x value. So my x is going to be natural log of 2 plus 1, or 1 plus the natural log of 2. Right, now why have I done it like that? What about all the modulus stuff? Well, doesn't really matter, because what we've discovered is when we're applying the modulus function, there are parts of the function that are preserved. So if I go back through the sketches, when we took the modulus of x, okay, the right-hand parts of that graph was preserved, okay? When we take, when we apply the transformation, the right-hand part of the graph is still preserved under the transformation. When we subtract 2, the right-hand part of the graph is preserved. So it's all where you'd expect. So I only have to really look for one of the roots, and then I can use symmetry. So I can see from the diagram here that this point that I've just discovered, as it's log 2 plus 1, means that the point here that I've just highlighted must be log 2 plus 1. In fact, I'll write it as 1 plus log 2. Okay. So that means that the difference between the 1 and the 1 plus log 2 is just log 2. So that distance there is just log 2. Okay, which means that all I have to do is subtract log 2 from 1, and then I've got my second root without doing any more fancy equation solving. So this root here, which I'm running out of space for, this is going to be 1 subtract log 2, because the distance is still going to be log 2 because of the symmetry. Right, so you might want to verify that on GeoGebra or Desmos or something. But that's an interesting exercise using transformations and the modulus functions. So please attempt the exercises, practice this, make sure you know your standard sketches, your parent functions, e, natural log, you know how to sketch quadratics. Yeah, and good luck with that.